And let's wrap up SRAM. So we can do the homework. What S stands for?
Static.
Yeah, static. DRAM. SDRAM. Synchronous dynamic RAM. So SDRAM is SRAM or DRAM. Yeah. For SRAM, how do we read an SRAM? So first, got this. Like this, right? This must be ground. I got a pair of PMOS, VDDs, and here's a signal. Let's see. Yeah. And this is a word line. It's called a word line. It's like one output from the decoder. If you turn on, you turn on these two NMOS. You select this row. So this is just one cell, right? There's so many of them. I mean, millions of them. And this is a bit line, and this is a bit bar. Like I said last time on Wednesday, it pre-charges. It turns this on because these are VDDs. So turns this on, which is you give a 0 here, right? Give a 0 to this signal. So you can turn on two PMOSes. That's going to flow charges to this point at the same time. It's going to charge it up to VDD. And then turn it off, so you can get two floating VDDs. And why do we have to do that? So before we read it, so keep in mind, I'm reading it right now, not writing it. I'm going to do the writing schematic later, but you have to simulate both reading and writing in your homework. But now that we're talking about this very simple circuit to build in your device. So when we are reading it, for example, it pre-stores 1, 0 here. So bit is the data to be read, right? So it's reading here. This is just another bit here. It can be used for other purposes, but now we are reading here. Bit. Recording. So charge it up to VDD and float it. So if you got a 1 here, 1 means it pre-stores 1. Is that a strong 1 or a floating 1? Strong 1. Why? Because the PMOS is on. It's always on. When storing that, it's on. It's a strong 1. And I have a floating VDD here. If the word line arrives, right, so the pulse arrives, it turns on these two NMOSes, turns on these two channels. Okay, what I'm reading here, what I'm reading from here, 1 is not changing. It's got 2 1s on the two sides of the NMOS, it's not changing. What if I have a 0 and 1 here? Why? Yes, and it's a strong 0, and it's a floating VDD, so it's going to discharge it. So the question is, why I'm not floating this line to 0, like floating ground, but it's a floating VDD. Or why I have to float it to VDD? Why it's not just floating 0, or why I just do nothing about it, just do nothing to it. So first, why I don't want to use a floating ground at the very beginning. When I'm resetting it, just floating ground to these 2 points. If I'm reading 1, 0, what's going to happen? Reading here, 1 here is a strong 1, right? It's a floating 0. What's going to happen? Your 1 is going to pass, right? But you are not passing the whole 1 because the NMOS is not able to pass the entire 1. It's like 1 minus VTHN, right? So it's bad. So let's pre-charge it to VDD. Then you can get the whole VDD. it's going to be a 1 later, right? So what do you have a 0, 1 here at the very beginning? If I float this one to 0, it's okay. Yeah. Got it? Okay. So it's better to float as VDD to VDD at the very beginning before you read it. So that's a reading circuit. Why, when I got a 0 here, this side has to be a 1? Why is that? Yeah, 0 will turn on this PMOS, so it's going to be a 1. What about this one? 0 will turn it off. It's a latch. No difference, right? Like I said, it's a latch. 2 inverters, 1, 0, 0, 1 is stable. It's a positive feedback, either 1, 0 or either a 1, 0 or 0, 1. Is there a chance that it's being stabilized at 2.5 and 2.5 volts on 2 sides? Ideally, probably yes, but it won't be that accurate. Whenever it's getting larger than 2.5, for example, it's 2.5, 0, 0, 0, 0, 0, 1, then it triggers that positive feedback. Then you are getting a 1. So the 1s, which is a little bit larger than the other one, will become a 1 later. And this one will be put down the ground. Okay. So when you run the simulation, you just need to modify the clock cycle here. And what about the values being stored as these 2 points? How could you assign an initial value? So there's a command in LT-Spice that I can use. You can Google it, how to assign initial value to in LT-Spice. Okay, but I'm showing you here, it's recorded. I'm showing you here, see? No. .ic, initial condition, .ic, and then V, capitalize the V, parentheses, and then the node. It's like initial value is stored in the memory cell. Because it's a reading, it's not writing, right? So you want to assume it's already being written. Have 2 states, right? 1, 0 and 0, 1. Just simulate 2, both of the conditions, and see if you're reading the correct value of 2 bit here, right? It's very simple. Any questions by far? The circuit, just 2 PMOSes and the latch and 2 switches. Okay. So this serves for the writing circuit. It can copy and paste and then adding more circuit to the writing circuit. And then I'm going to draw that writing circuit to you guys right now. How to write into a SRAM cell. Here. So the SRAM is being used for what? The RAM card on the computer, plug into the computer? No, that's DRAM. Flash is something different, right? Programmer, yeah, for CPU, for cache. It's expensive, it's more transistors, and it's fast because of the positive feedback. And that's why you don't want to use like 4 gigabytes or something. Use SRAM, it's too expensive, right? So for the writing process, somewhere on the top. here. Same gate for these two transistors. That's a word line. This is a write command. And here's data. How that works. Pre-charge the same cell, so it need to be read and being written at different clocks, so you couldn't get rid of it. So this one can be written and can be read. So how do you write a 1? So if data is 0, for this one, right? If data is 0, and when write, the write command is 1, what's going to happen? It must has an initial value. So when you are running a simulation for this cell, you have to assign initial values to the memory as well, because it's going to store something here at the very beginning. Okay. So here's a bit line, right? That's bit. If data is 0, here's 1. And when write is 1, these two, both of the NMOSes here are on, right? So this is 0. If it stores 1, 0 here at the very beginning, is it changing anything? If 0 comes here, is it changing anything? It's not changing anything, right? So it's writing a 1 to bit. Data 0, but you are writing a 1. You just need to invert data, right? Data bar is 1, so you are writing a 1. Just invert it.
It's a complicated circuit.
Oh wait, so the reading part.
Word line.
The word line just turns these two on, right? So the data can be passed to the storing the latch, to the latch. For writing, for you turn it on, you have to, for reading and writing, right? It just has to be on when you are doing something to the latch. It's like another signal container outside of the latch. Yeah, so word line has to be 1, right? So when data is, you know what I mean? So I want to do this, data bar. Okay, so data is here. So this data inverter, data bar. So when data is 0, so in this case, data is 1, right? I'm going to give you all the different cases. When data is 1, after the inverter, data bar is 0, and this is 1, turns this on, NMOS, and because the writing is also 1, so both of the two NMOSes are on, it's going to be discharged to ground, okay? And because the word line is on, is 1, so 0 will pass through here, and it previously stored 1, 0, so it's not changing anything. So when you're, so it's writing a 1, it's not doing anything, but it still is. It's writing a 1 to it. Because it's not changing, it's still 1. What about 0, 1? If it stores 0, 1, what's going to happen? Yeah, so whenever this is on, because as we analyzed, previously, right? So this becomes 0, and it's a strong 0. It's a strong 0. So it's going to discharge this 1. So you are saying, hey, this is a strong 1 as well, right? What's going to happen? It's going to compete. So how do we, because you are writing to it, so you want to win in this competition. So which should win? 0 should win. So you want these NMOSes to be wide or huge. So increase the width. Okay, so you got a strong pipe to pull that node down to ground. But when you write it, you need this one to be even wider. Yeah, so these. This one? This one is just a switch. Just a switch, yeah. Got it. So you have to make this these two NMOSes relatively larger than these PMOS, stronger than the PMOS, that is able to pull it down to ground. So if this one,
I just have a hard time when I pick sizes for like gates and stuff. I feel like I'm just picking
values. Most of the times it all works for digital. Just depends on the driving capability. I think this is probably only one consideration when you are sizing them, just driving capability. But in analog, there are millions of considerations to size them. If you change a little bit, the gain changes and it's stopped working at all. So, but in digital, because it's just 1 and 0, so it's not really sensitive to sizing. But when it's getting sensitive is because you got, for here, right? This is a digital circuit. If you have tiny NMOSes, you just won't be able to discharge it. Yeah. So you have to make it big in order to discharge it, not driving it, but discharge it. But when you are driving a bigger circuits with a lot of capacitance, so we analyze all the capacitance of the digital nodes, right? Remember the mirror effects, you have all the caps around the gates. So when you have huge transistors to be driven, and you need huge transistors or huge gates to drive these huge ones as well, because you need a lot of current. You need a super wide channel connect to the ground and also to VDD. So you can dump a lot of charges and also discharge it, drain it as well to the ground. So if you got it's previously stored 0 and 1 here because you have strong NMOSes that is able to discharge it and flip it, right? Because this is the latch, if you flip this node, here will automatically becomes 1. It's inverters, right? It's gonna work. So this is how you write a 1, right? Data is 1, so I got a 1 here. Make sense? What if data is 0? No. Oh, for this one, hey, if data is 0, you should get a 0 here, right? If data is 0, data bar is 1, and this is 0, right? And this will be turned off. And it privileges the charge to NO. If it previously stores 1 and 0, what's going to happen? This will be on, right? Yeah, this will be on, then it's going to pull this down to 0, so it'll become 0. It will, because it's the latch, so whenever this one is being flipped, this will flip as well, right? Like on, off like that, right? Okay. Make sense? So one more thing about the PMOS from yesterday, you may have figured out as well, but I just want to do it really quick. So for that switch, this, right? This thing. I think we should trust science, right? Right? Should do that.
Yeah.
Nothing wrong with that. Nothing wrong with that, but something is wrong here because, oh, these shouldn't be shorted, right? So this, yes, you can short this to VDD, but I will still do this. But I'm going to invert it, you know what I mean? Yes. Yeah, because for example, previously you got a VDD here, right? That's why he has to put a VDD here, because when you got a one, you want to turn this on, so you want to pass a one here, right? If you flip it, you got a one to turn it on, but it's passing zero, so it's wrong. You know what I mean? So it's okay if you have a one, but you don't invert it. You got a one here, and but you have to have a VDD for the NMOS. Let the NMOS to pass VDD, which is not ideal. We don't like it, remember? So if you want VDD, if you want NMOS to pass zero and PMOS to pass VDD, you got to add an inverter here. So whenever one comes, you want to add a one to it, right? It's going to be inverted. So this one will be on. So one will pass. You are getting a one here. So one here, which is good. Try yeah. I know. I think the sizing, the driving capability here matters. I don't know what's the sweet point or which part really need that driving capability. If you make this inverter a huge inverter, so it is able to drive, turn on the gates more efficiently, so you can pass the one to here. Mm.
I was getting like 10 for my whole circuit.
Yeah. Yeah. But this one definitely clears up something, right? And in addition to that, I send you a link to the GitHub file. I think that one is the whole design of the ADC, the SRAM ADC.
Yeah, but the problem with that one is the switches are hidden, so we can't really see.
They do have schematics. Just dig into the files. I know that's a symbol. But there are the details of the circuits in some of the other files. Have to dig into the folders. Yeah, it's a whole design. It's an entire design for everything. You are supposed to be able to duplicate it, I think. That's the worst case. Let's try that one. Maybe that works, right?
Also, I was kind of confused at his CDAC. It had a weird symbol that I've never seen. It was like two triangles and then a circle in the middle. And the right side is weird.
Yeah.
I don't know what that is.
Yeah, we still have time. So just study it a little bit, right? Still better than just duplicate whatever we have done.
Yeah.
It's just explore new things, and hopefully there will be some new findings. Okay, you guys are ready to talk about your design or findings?
Yep.
Good.